Hey guys, this is Saptarshi here and welcome to our YouTube channel. Last video tutorial, we have discussed about recommender system, its different types and why it is important. Today we are going to discuss one of the approaches of recommender system, namely collaborative filtering. So collaborative filtering can be divided into two categories. One is called as user-based collaborative filtering and another is called as item-based collaborative filtering. Let's understand this with an example. So let's say this is a movie recommendation system and we have certain user who has watched movie M1 and M2 and has liked them. So he has given a good rating to these movies. Okay, and by some means I find out that there are a couple of users who are very similar to this particular user. How do you find similarity will come in a while. And this person may have watched movies M1 and have liked it, and also have watched M5 and have given it a good rating. Similarly, this user may have watched M2 and also have watched M8 and have liked both the movies. So what should we do now? I know this, these users are similar, and this guy has not watched M5, so let's recommend this to M5. M5 to this user. Similarly, let's recommend M8 to this user. Okay, so this is how user-based recommendation works. All right, and what about item-based recommendation? So in item-based recommendation, I know that this user has liked this movie M1 and M2, right? So I'm only going to consider the movies he has liked. So the ones shaded out, these two, assume that he has not given a good rating. Now from the movie data set, I am going to find out similarity of movies with M1 and M2. So let's say I find out that M10 is quite similar with M1. So what I will do now is I will recommend this back to the user. Okay. So this is how item based recommendation works. Alright. Now let's look at types of collaborative filtering. So basically from approach point of view, it can be thought as a memory based approach, where you deal with the entire matrix and generally you can store it in the entire memory. So these are also called as neighborhood based models. Okay. And other approach is called as model based approach, which either uses any machine learning based model or some matrix factorization methods. Okay. So we'll come to that in later lectures. Alright. So now let's now look at the maths of the neighborhood based collaborative filtering. Okay. So we want to recommend, but how do we recommend? So let's do some recommendation for user 3. So I already know that these are 6 items. This guy has already taken this item and given some rating. However, he has not taken 1 or 6, right? So if I have to recommend him, I will try to see that which one I will recommend to him, 1 or 6, something of that sort. Okay. So this problem of recommendation can be slightly modified. So what I can try to instead find out is that what could have been the potential rating of the item 1 by 3 and what would have been the potential rating of the item 6 by 3. Okay. So whichever has got a higher rating, I recommend that to the user, right? So as you remember, we are going to find similarity between users. So how can we find similarity between two random variables? We can find that using simple Pearson's product moment correlation coefficient. So let's just use that. And instead of using all the ratings, we are only going to use the rating or only going to use the items where both of them has given the rating. So here when I am trying to find out maybe correlation between 1 and 2, this third element will not be considered in the calculation. Okay. All right. So if I apply this on this data set, the correlations that I get are something like this. Okay. And if you remember that correlation basically varies between -1 to +1, and +1 means that it is completely identical. So you can actually ignore this one because it is correlation with itself. Autocorrelation is always 1. So then if I look at these 4 values, I can understand that these 2 users are most similar to user 3. Okay. So I should use the rating of these 2 users to find this rating, right? Rating of these 2 users. Alright. So one of the simple thing is to do a simple average. But instead of simple average, what we can also do is we can use the similarity and use it as a weight, something of this sort. Okay, so I can use that, and I get that the potential rating is 6.49 for the first item, and for the 6th item it is 4. So if I have to recommend one between the item 1 and item 6, I will of course recommend the item 1 to him. Okay, so there is a little bit of a problem. The problem is that different users give different scale of rating. So what do I mean by that? So let's look at user 1 and user 5. So user 1's range is lowest rating is 4, highest rating is 7. And if you look at user 5, the lowest rating is 1 and highest rating is 3, right? So it is very unlikely. So now let's look at the user we are most interested at, user 3, right? And you see that the lowest rating is 1 and highest rating is 3. It is very, very unlikely that he is going to rate this one as 6.49 and this one as 4. It's very unlikely. What we are going to do? We are going to mean center the rating. Okay, so what do I mean by that? So for each user, I find the mean rating. So I will sum them up and average them, right? And then I will subtract the mean rating from the individual ratings. All right. And then I will use the same formula what we were using earlier. So it has been made more general. Okay, instead of directly using correlation coefficient, we are saying we are using similarity between the user. Okay, we are using similarity between the user, and if you look here, I will have to add back this mean rating. Okay, all right. So now when I use this revised calculation, the rating that I obtained for the first item is 3.35 and 0.86 for the last item. So now at least you are sure these are more realistic, right? These are more realistic, and now you are completely sure that no way you are going to recommend the item 6 to him. And 1 still has a good rating compared to his own ratings. Okay. So this is how these small things can go a long way to handle this kind of tricky problems. Okay. There is another problem that we face, which is called the problem of long tails. So this means that there are some items or some movies which are rated by almost all users. Okay. And then there are several movies which are rated by relatively small number of users. Okay. And this follows a curve like this. So, this x-axis actually gives you number of movies. Okay. And here it is given that the number of ratings a movie has received. Okay, so there are some movies, if I go somewhere here, maybe around 100 movies which has got a good rating, and once maybe you see from 5,000 to 10,000. So all these 500 movies, okay, has got less rating than 20 or 25. Even if I just draw a line over here, let's say something like this, okay. So this can be something around 40. So all these, right, after 1,500, all these 85% movies has got very, very less rating. So what is the problem with this? The problem is when I find users, okay, when I find user based on their ratings, so only these ratings will be considered, right? So their ratings on all other items will not be considered. And this problem is very similar to something like compare to sentences. If I am trying to compare two pieces of text and only common word between them are and the, and based on that if I say the piece of text are similar, then our logic is not right, isn't it? So same thing happens over here. If there are two users and their only rating is available for a very popular movie, and on the basis of that we say they are similar, that is not a correct logic. All right. So we do some kind of a discounting. How do we do that? So basically we find out that how many users are there. Okay, so M is your number of users. Okay, and how many users has rated that particular item. Okay, so this has kind of a inverse effect, if you see, right? And this gives a weight, and this can be used now in the rating calculation. So only thing that you see has got changed over here is the weight that we have added. All right. Okay. Now let's look at some other similarity based measures. So one of them is cosine based similarity, and you already know about cosine. So the numerator is an inner product, and in the denominator you find the norm of each of these vectors. This can be considered as vectors, right? And divide by that, right? So this is raw cosine. You can also do an adjusted cosine. So adjusted cosine is when you have mean set at the rating, and this can be very easily extended to item based recommendation. Okay, so what the calculation that we have seen in detail is for user based recommendation, but like we found similarity between users by the rows, I could have found similarity between the items using the columns, and then based on the potential ratings I could have recommended something back to the user. Okay, now let's look at some of the characteristics of this item based and user based recommendation. Item based recommendations are more accurate, okay, because it is based on that user's own experience, whereas user based recommendations are more diverse. So you know that for a recommendation system you don't want to be only accurate, but you also need to bring some flavor of novelty and serendipity, because if you make obvious recommendation to the users, that may not be exciting at all. Okay, also let's understand a phenomena called as shilling attack, which happens in recommendation system, where lot of fake profiles are created and then rating of certain items are inflated or deflated. Okay, and if it is a user based recommendation, it can be affected a lot, but for item based recommendation it is more robust to this kind of attacks. Now, I am sure you understood how simple these methods are, based on only measured similarity by correlation coefficient or cosine difference. However, this has very high time and space complexity. Okay, and actually it is quadratic. So if you have 10 to the power 5 or 10 to the power 7 users, which is not a very high number of users in a large scale system. Okay, so the amount of time that you are going to take is 10 to the power 7 square, which is 10 to the power 14, which is a very high number. Okay, and another question that can come to your mind is that, can we not combine user based and item based? Yes, of course we can. So what we are doing is we are not looking at all users, but we are trying to find k similar users, right? Or k similar items, right? So instead of using k similar user and k similar item, we can actually generalize it and say k most similar users or items. Okay, so in that case, I may have got a rating of I may have got a rating of 5 from my nearest user and 6 from my second nearest user, and then a rating of 4.5 from the item based similarity. So assuming simple average, I can just sum them up and give the final rating, right? So a combination is definitely possible. All right. So there is also something called as a clustering based approach. So as we discussed that this has a very high time and space complexity, and generally you have this rating matrix or preference or utility matrix, right? So in clustering based approach, what we do is that in ordinary method, you go to this entire rating matrix and find that top k similar users, taking the user based CF as the example. Using clustering, what you do is you create separate clusters, right? These clusters means that users in these clusters are more similar to each other. Now let's say I want to find rating of a particular user, and I know that that user falls in this cluster. So what I'm going to do is I'm not going to search the entire rating matrix. Rather, I'm going to concentrate only on this cluster and find the k users from here. Okay. So this is one of the advantages. Some of the challenges of clustering based approach is that, of course, there are missing values, right? So there will be a lot of items which are not rated. And another problem is that how to decide the grain of the cluster. So one side, the size of the cluster can be like, as big as the entire data set. On the other hand, it can be as small as maybe 2 or 3 users, right? So it is a trade-off that we need to take. All right. Another type of method which is called as matrix factorization. Now matrix factorization is a method which is used in many of the techniques, right? And collaborative filtering, we said we are discussing today the neighborhood or memory based approaches. So we will see in later lectures that matrix factorization can also be used in model based approach. Okay, so let's not get confused there. So what is the concept of matrix factorization? So you already know factorization for a number, right? So you have smaller numbers, and when you multiply them, you get back the original number. Matrix factorization, concept wise, is no different. So here I have a rating matrix, and what I am trying to do is I am trying to find two smaller sub matrices which I am calling as U and V, okay, which when multiplied will give you back or approximately give you back the rating matrix. Okay. Now please see that this matrix U has the same number of dimension or same number of users as that is in the original matrix, and V has same number of items that is there in the matrix. So I can think of that this is a new kind of vector representation, okay, instead of this representation of the user. And same goes for the item based, or same goes for the item based matrix. Okay. So this is called as a user based embedding. You already know that projecting a higher dimension vector to a lower dimension vector is called as embedding. So this is called as a user embedding matrix, and this is called as a item embedding matrix. Now let's try to understand that how do I find U and V. So as we do in all machine learning problems, what we are going to do is we are going to use an objective function. So basically I am going to multiply this, I am going to multiply this matrices, okay, where I will need to take a transpose of this vector and multiply, okay, and I will get an approximate rating. All right. So what I'm going to do is I'm going to get this approximate rating, and that should be as close as possible to the actual rating. All right. And how can I do that? I can use our simple mean square techniques, right? So this is your original rating, and this is the rating you are getting by multiplying these two sub matrices. Okay, and I am taking a square, summing it up, and for the observed ratings, and then I want to minimize it, right? So this is an objective function, and you might have noticed that even for the unobserved items, right, you are getting some rating. Okay, so I can include that in the objective function and make it more generalized. Okay, so this is the items which are observed or has been rated, and these are the items where it is not rated. And now I am trying to minimize both. So this also has the same form, right? But here, as the rating is 0, this is not mentioned over here. All right. Okay. So this is what we are trying to minimize over here, and W0 is how much weight you are going to give to this particular type of deviation. So this can be thought as a hyperparameter. Okay. Now, like all machine learning problems, we can solve it using stochastic gradient descent. And there is a particular type of optimization algorithm called as weighted average least square or Walsh method, which can be used for finding this sum matrices. Okay, so SGD has the flexibility, so it can cater to many loss functions. However, it has slow convergence and not good for unobserved items. Okay, all right. So that brings us to the closure of memory based collaborative filtering approaches. So we discussed how this can be converted to find out the potential rating for the unrated items and then recommending them back, right? And user based recommendation and item based recommendations are very similar. It has a very high time complexity, so you can go for clustering based and matrix factorization based methods. Thank you so much guys for watching these videos. If you find it helpful, please generously like, subscribe and comment. Thank you so much guys.